everyone, my name is Thomas, and I'll tell you now about the feature I've been working on for a year, and it will be soon to PhD, I hope. So I've worked together on this with my supervisors, Dominique and Frank, as well as transcribers, both from Belgium. And so what is a partial type signature? So I think we've all been in the scenario that you're writing a program, probably something with a file, and yeah, you know, you probably need to do statements when you do something with a file. And then you're writing a program, and at a certain point in time you get stuck. You don't know what does this value mean, what is the type of this value, or what is this function that I have to use. And thankfully, since GHE 7.8, we have a new feature, typed holes. And we can just insert an underscore, and then type to your program, and compile a complaint, and say, oh, we found a hole in your program, and it has this certain type. We'll give you some hints about relevant bindings. So you see, okay, this is this type, okay, I can fill it in, you fill it in, you continue. Okay, this is all nice and well, that's already implemented, of course. But what about the type signature? You know, it's probably IO, because you have the file, so what is return type? Wouldn't it be nice if you could also write this, just an underscore in the type, and then let the type checker figure out for us? Because essentially that's what the type checker is for, to figure out types for us. So that's what I've been doing, and that's a partial type signature. So now, or in my branch of course, you can write an underscore in your type signature, and then the type checker will infer a type for you. For instance, in this case, yeah, just free lot. And what's better yet is that we don't even have to fill in the type, because unlike the type tools, which still have some opportunity of choosing which value, there's just one type that can be inferred here. So when you enable this new extension, partial type signatures, you don't even have to fill it in, the type checker won't complain, and that's it. Okay, the rest of this talk will just motivate my proposal, some examples, and then we'll work through the syntax, and I give some insights into the formalization, and then discuss the implementation. Okay. So currently, we Haskell programmers face the following dilemma, or at least the users of GHE, not the UHC users. Do we write a complete type signature, or none at all? So wouldn't it be nice if I compromise, like a bridge between two opposites with extremes, and that is partial type signatures. So another small example, here is function foo with type signature, and you can match the annotation or mixed annotations with your inferred types, different values and underscores. In this case, this bool type annotation gets propagated through X argument, and this is the final inferred type. So essentially what we're doing is giving us more flexibility between the type checking and the inference. We have more control of what is being type checked, like this bool, and what is inferred, like this underscore. A use case we propose is during development. You're constantly changing your function, but of course there are type signatures as well. So what you have to do is update these type signatures. As we all know, we programmers, we're kind of lazy, so we just scratch the type signatures away, and we proceed without type signatures, or at least some people. And the problem is then that you lose the valuable documentation, because you could just glance at the type signature and figure out the type, instead of having to use manual or mental type inference. And also you use a checking part, so the JIT signature verifies if you're already correct in this program. Thus, we could use partial type signatures for that by annotating the fixed part and leaving out this fluctuating part by writing an underscore. And this leads to a related use case that I've already shown in the beginning, which is when you just don't know the type yet. So this facilitates an active style holding driven development level. For instance, this function var. We know the second argument is a tuple of a character and an int, but after a week of ICFP, we're just too lazy to figure out the rest of the types. So we just write some underscores and let the type inference engine do it for us. In this case, it says, oh, first hole, it's a function from character to int to bool. We'll fill it in. Next up, we'll figure out, oh, this is a bool, and that inference engine has done everything for us. Even better yet is the work that Alejandro has done during the summer. He's already added support to Emacs for role-driven development, but that's just for the type tools. And I've talked to him, and he said to me that it basically just works as well with partial type signatures. But it would be nice if we could extend it even further to interactively fill in these holes. So we don't have to type them manually again. And even better yet is that we could just, when we're really lazy, write this pragma, partial type signatures to just let the type checker figure them out for us and don't complain about it anymore. So another use case, you see this function which is quite complex. It's from Boolean Micromotor's grammar combinators library. You see sometimes the type is so complex that it obscures the essence of the type. For instance, you have these constraints. It would be nicer if you could just omit them, so we could write the type an extra constraint. Or types which cannot be inferred, like rank types. So I have this function here foo, and it takes an argument and applies it to two lists of different types. For instance, we could apply it with the reverse function. The problem with this is that the type can be figured out by the type checker because the argument is polymorphic, which results in a high rank type. So what we have to do is write out the full type signature. And in this case, we're also forced to write out this type, this part of the type, which could easily be figured out by a type representative. So we're doing extra work now. So it would be easier or lazier to write this. Okay, I'll now walk through the syntax we propose. So this is standard filter functions, and the example I'll be using from the preludes. So just keep in mind this type signature, you probably don't know it by heart now. What if we write this? We replace the bool type with an underscore, same type gets inferred, no problem. What if we write this? We replace the a, that's also no problem. We can just as easily unify type variables. Or we could even just omit the whole function. Functions can refer to. We could mix and match and continue and write this. So we only enforce the type to be a function with two arguments. Or we should just lease one argument, because this can unify with another function type. Or just this. And this is actually the same as I think I'm doing. Next with named wildcards, which are useful to enforce that two unknown types should be the same. So in this example, I'm going to replace everything with underscore x. What happens is that the type checker sees, oh, this must be a bool, so every instance of underscore x will be a bool. We get this type. But if we omit this one from the underscore x series, so the type checker sees, oh, we can just easily generalize it, and we have the same type as before. But now we use the W prefix to indicate that it's a type variable, and not a named wildcard, and let we reuse the suffix. Another small example, in which case we clearly demonstrate the usefulness of named wildcards is when you have an unknown type. Perhaps, and this example is a bit silly, but you get the point, I guess. An unknown type, but you know that at least has to implement this type class. So if you write down like this, and it's going to figure out the same type as before. But if you wrote this, it would figure out, oh, it's a bool, but bool already implements each, so no worries. Show it going. Next up are constraints wildcard, which you just saw here. This I call a constraint wildcard, occurring in the constraints part of the type. There's a problem with them because type checking doesn't really, or type inference doesn't really work like that. So see, have a look at this example, bar, just like E before, but we have this ORT constraint, which is a superclass, of which E is the superclass. So this is perfectly fine. But if we write this, what would happen? The type checker would infer each, and it has in its context its available constraints in for instance for something unknown. And it just doesn't match up. It doesn't work that way. It doesn't try to unify constraints in some places. This won't work. Another example, we have this function which increments its argument and displays it. If you write this constraint, do we for show or do we for num? So okay, we don't allow it. We just but we do find one case in which it's useful when we have named wildcards in the constraints, and they're also present in the rest of the type. So this won't work, this won't work, but this will, because the underscore x variable for wildcard will be unified by type inference here, and then it will also be okay when it's used there. Okay, then the last kind of wildcard, which might be one of the most useful ones, is the extra constraints wildcard. And I'm going to look at this example, which is roughly the same as one before. So now we can write a wildcard in the constraints, but not in the constraint, but as a constraint. It will become more clear in the next example. But what then happens is that any number of constraints can be inferred. So this could be 0 up to not infinity, but a high number, of course. And we can also annotate some part of the constraints, in which case only one constraint would be inferred. And this other example is just a show function. If you write this constraint, we have this as we would expect. But if you write a constraint, which would not be inferred by type inference, in my opinion, it's best to have this final type. So you don't get a surprise that Simon has proposed simplification. I mean, for the implementation, it's much simpler like this. But to drop this constraint, the annotated constraint, I find it kind of counterintuitive. Maybe people have differing opinions, which tell me about it afterwards or after. So I would propose to still go with this instead of dropping the annotated constraints. Before when I saw this, we have some typing rules as well. We looked at the outside-in type system, so we modified those rules. We have some proofs about it as well, and we presented it in a file in January this year. So I'm not going to really show you all the typing rules. It's the end of the week. We don't want to see that anymore. So I'll just give you a small example that will explain the idea behind it all, which is actually quite simple. So let's see if this function second arg, it just returns the second argument. We have this partial type signature. The basic approach is to ignore it and do regular type inference, but enforce the shape of this partial type signature. So let's do that. Type inference. We encounter some unknown types, and then we use fresh unification variables for them, alpha, beta, and gamma, which results in this unknown type here. Then we do constraint generation, and we walk through the quality function, which is very simple. We just have one constraint. The type of the argument of the second argument must be the same as the return type. We have this constraint, we solve it. We have a solution, which is the substitution. We apply it to the type. We have this one. And then we generalize over it because there are 3 unification variables left. Then we have this one, which is the most general type of this one. Now, the partial type signature. How do we deal with this? How do we enforce this shape? Now, the idea is actually to, just like these unknown types were replaced by fresh unification variables, we can do the same with these wildcards, which are actually also unknown types. So the basic idea is to replace them. In the formalization, we call this the desugaring. And we use these omegas, 1, 2 by convention, which are just the same like alpha and beta. Then we add an extra constraint, which just says that the desugared partial type signature must be the same as the preferred type. And we solve this, we have the substitution. We apply it, we have this type. We generalize over it, and we have the type that we apply. We prove some theorems in our paper. For instance, we say that it's a conservative extension, so your function doesn't use partial type signature, you won't notice it. Also, we say that this partial type signature, which is just the extra constraints wildcard, which means that any number of constraints will be inferred for regular type wildcard. This is basically the same as writing no signature at all, and so fully rely on type. And this is correct. And also samples shown. Okay, I'll give you some insights in the implementation. So we have partial support for wildcards, and the first hurdle we encountered was that the named wildcard syntax we thought of was clashing with type variables. So currently in GHE and Haskell 2010, this is parsed as a type variable. And this program won't work as we want X to be a bool. So we get this error. And our idea was to just add an extra extension named wildcards. to remain backwards compatible. So maybe there's another solution, maybe use some other syntax, but this was the most intuitive form.
What about using just apostrophe, the same way you lift terms into types, you could lift wildcards into types?
Wait, but how do you name them in that case? So,
apostrophe underbar A.
I won't that conflict with the word which is
Oh.
It's to merge first.
Next, we don't allow these wildcards in some types. For instance, in the signature of a class definition, it wouldn't be very sensible, or in this instance, so we disallow them there. And then basically we quantify these wildcards per type signature. This is the data structure in the compiler for the type signature. And we follow the scoping behavior of the scope type variable extension. So this program, we have this function foo, which takes an argument, which must be bool, because we bind not to it. And we have a local binding, which is basically the identity function. We apply two characters. So if the underscore A type wildcard is the scope here, that would be a problem because it's forced to be a bool, and here it's used as a character basically. So this won't work if the scope type variable extension is enabled. But standard it's not enabled, so this will work. This is not a bad thing. Just to explain, there is a difference when you enable this extension.
It's not a scope type variables, any scopes of things, or you mentioned an explicit for all.
Yeah.
You say foo colon bool underscore A blah.
Yeah, yeah. So the problem is here we're dealing with named wildcards which don't have this for all scoping construct. So
and you don't want them to scope.
we won't usually be able to scope them.
Oh.
So when you enable this, it will scope automatically. We could think of a for all
say
construct as well.
exist underscore A.
Always scope.
Scope all the things.
So it's open for debate, of course.
And it should be exist.
Sorry.
And a clever idea that was already being used by the type field extension was when type checking to report the instantiated types of the wildcards. We generate these insoluble constraints between the wildcard unification variables, these omega-convenience, and the inferred types. So because they're insoluble, they will be left over after the constraints over has run, and we can then easily convert them into messages. Unless we enable this extension, we just would allow them in the first place, so we don't generate these insoluble constraints. So the code is online. There is already a fabricator code review going on, and the practical business food. So please have a look at it, code review. Good practice your fabricator skills. Thank you.
Could you go back to the slide where you had the partial constraint word underscore, but the algorithm gave you equal A. Right, so I would expect the following stronger property of your thing. If you have a valid manual type signature and you replace arbitrary parts with underscores, your algorithm still says this is a valid thing. So basically, I guess what you're missing is you need kind of a subtyping for these constraints. I mean,
the problem is that there is no unification going on with the constraints.
It's not subtyping, there's an implication.
Yes, yes.
Right.
Yeah.
So this is like
The constraint solver is aware of the implication, but constraints aren't solved by unification. It just checks if there's a perfect match in the context, or it uses these subclass relations as well. But if there is only a vague partial instance, it doesn't have to match it.
But computation sounds like a good one.
In principle, the OR would be a correct type.
Would be enough, yeah.
So I think you keep the OR because maybe later someone, as I later I want to extend this function, and then I will use these the But it won't force him to first invalidate something he's sure about.
Yeah, I see your point. But there's other cases in which the type checker would have to guess which constraint to unify, and you don't want to guess. As Richard said, guess free. Right.
Also,
I say, take the hints which are there and don't guess this.
You mean don't guess with this one? Or,
No, you just, it will be ordered.
Yeah, but order once. That's the
Yeah.
problem.
Yeah.
yeah, if there is
Yeah.
A and B, when should we
Yeah.
go there?
So you go to the higher rank sample. Or maybe so the way you presented the formalism, you said first we infer the type and then we check it against the
Yeah.
holes.
Yeah.
Well,
I thought the same at one time.
doesn't
Then
work
I
like
figured out you get some unification variable at this place, sort of. And by unifying with, or adding the constraint between the inferred type, which will contain just the unification variable here, you force the type hint to unify with the unification variable.
follow up. What happens if you put underscore for one of the A's?
I have tested this as well. I think it works. It just works.
Okay.
So just quickly, because for all you write that manually. But when you do that,
Sure.
it's pretty much okay.
Yeah, I was just expecting some tricky corners because you have a
Yeah, that's a tricky point.
and that's a an unknown type that might depend on some.
If I have an extra wildcard constraint, will that ever infer equality constraint?
We have looked into enabling this, but we disallowed because you could get constraints like int must be equal to.
Yeah, sure, I could write the identity function as underscore double arrow A to B.
Yeah. We disallowed it.
Okay, one more question.
If I have a function that's running in the monad and returning, say, a bool, can I use underscore bool after as a return type?
Yes.
And can I do that even if it's not just IO, but rather state T S IO, like a state higher order unification thingy?
Yes. Oh.
Weird.
You have to have that. I think so.
Okay, the chairman of this session has to catch a bus. Thank you very much for the contribution.